Hey NA Physics, it's Mr. Neff. Today let's talk spring potential energy. But before we get started on that, why did the carpenter quit using the drill? Watch to the end of the video and I'll tell you all about that. So I found this nifty simulator over at PhET, and I'll put a link to this in the comments. It's the Hooke's Law one. When you open this up, you get some options. The intros were great. See what it does. Gives you a robot arm that can grasp and stretch or compress a spring. You're allowed to put the applied force, show the applied force, the spring force, the displacement, and the equilibrium position. All really important parts. So if you grab the robot arm, you click, you start to pull, you'll get some little forces. So the blue one is the spring's force. The orange one is the force that the robot arm is applying. I'm going to call that the applied force. And you can see that green vector down there is the displacement at the end of the spring. If we let go, if we would let this go back to zero, or basically zero, we would have no force. Now you remember from our work with springs that the more you pull a spring, the more the spring resists. And for, well, say 17.3 newtons, then there's a spring force of 17.3 newtons, and you can see that those are going to be even Steven as far up as you go. Now this only lets you go to 100 newtons, and you can see that 100 newtons will stretch the spring half a meter, and that would let you calculate the spring constant. And you can see that that's 200 newtons for each and every meter, and we only can do 100, so we can only do half a meter. Now you could make a graph of that, and we have in class already. We stretch a little and we get a compression, we get just a little bit of stretch, and we do a little bit more and we get some more, and I could make a graph of force versus stretch, and this is really famous. I could also do it for the compression side. It'll let you compress the spring, and the spring doesn't like that either. See how it resists? Okay, so what I want you to do, I want you to pause the video right here, and I want you to make a graph of applied force as a function of stretch and spring force as a function of stretch. Pause the video right there. All right, I bet you did a nice job with that. Now over on the energy tab, and you could see that on the bottom if you go over to this, you can see that they show you the spring and now a graph. And they'll let you do bar chart, energy chart, force plot. I'm going to do the force plot. And sure enough, here it is. So for this size spring, it will, if I pull this much, this much, this much, it'll displace that much, that much, that much. You can see we can put the applied force on there and the displacement, and we can even see the values of what they are. And so you can see that, and this is not the same 200 Newton per meter spring, but as you can see, this is 100 Newton per meter spring now. And all that to say, the graph of applied force, as I asked you to make, versus displacement, well, it looks linear. These over here in the first quadrant would be when we're stretching the spring, and if we're compressing the spring, you can see that that's down here in the third quadrant, where the displacement at the end of the spring is negative. It's just off the screen so you can't see, but I can slide the spring constant up, and if I do that, you can see what happens. It gets steeper. And so the point of this video, though, is not just to cover spring force, because we've already done that, but now to cover energy. Now, somebody who knows what they're looking at can actually say, ah, I see the energy in that graph too. Where would that be? Well, they let you click the energy, and there's kind of a little legend here that shows me what to expect. If I click that, it fills in a blue area between the x-axis, the displacement axis, and the graph. Maybe some people would call that an integral. Now, does that really mean the energy? Well, let me take a quick screenshot of this, and then I'm going to try to show you that it does. All right, so check this out. So we have a triangle here, and it looks like they're suggesting that that area, or that integral for you calculus types, is the energy stored in the spring, or even the work that we did on the spring. So let's see if we can get behind that. We'll say that this dimension right here is the stretch of the spring. Right there, we'll call it x. And I understand that it's negative, but I want to try to make something that's good for always. And then what's this dimension right here? Well, it's the height of the triangle, of course, but it's also the force that it took to get there. Now, the force had to keep growing as you went along here, naturally, but now what I'm seeing is that it is the force that it took to get that far. So if I were to multiply those two together, I would do something like half of some amount of newtons. It looks like it's 340 newtons times that base. And it looks like it's 0.850 meters. You're probably looking at that negative, and so am I. But the force was also negative, so I'm just going to ignore the negative and the negative that I would be placing there. Okay, so if you go ahead and multiply those three things together, the half, the 340, and the 850, you sure do get 144.5. And then I have newtons times meters, and you've done enough of this to know now that that is joules. So that does lead me to believe that that's some kind of energy. Now, the other thing you could do if you were saying, well, is this the amount of work that we did? Well, yes, this is the amount of work that the spring did, and this is the amount of work that the robot arm did as it was compressing this. The spring pushed to the right as the compression went to the left, so we could say that the spring did negative work, and the robot arm pushed right while the displacement was the robot arm pushed left while the displacement was to the left, and so it did positive work. So all that to say, that area does seem like it represents the energy stored in that spring and the work done by two things. In general, we could say that area, or now we think it's the work, is equal to that maximum force times the displacement. Or I could make it 1/2 times whatever that maximum force is times that displacement. Now, we know how springs work, and we know that the force that you need to do a certain compression or expansion is kx. And so I have kx for the force plus another x from before, just because of the geometry of the triangle. And so I could say that the work done here, the energy stored in there, is 1/2 kx squared. Now, that value can appear either positive or negative. If you said to me, how much work did the spring do? Well, remember, the spring resisted this, so I'd say that the spring did negative 1/2 kx squared. How much work did the robot arm do? That's going to be a positive 1/2 kx squared. And how much energy is stored in the spring? And that's probably the number one reason why we're talking about this, and the amount of energy stored in the spring, or the amount of spring potential energy, is 1/2 kx squared, where x is how much you've compressed or stretched that from equilibrium, and k is the spring constant for that spring. So we're going to see how this works in response to other forces and amounts of work and other kinetic energies and so forth in the future. So let's practice it and get good. And before you do go, why did that carpenter stop using the drill? He thought it was always boring. See you next time.